of a parallel plate capacitor is C is equal to epsilon A by D. What is the epsilon? Tell me.
And permittivity.
A.
Area.
E.
Distance between the two plates.
E is this separation between the two plates. Right. D is the separation. This separation between the two plates. Offered capacitance by the parallel plate capacitor, we can calculate by using this equation. Epsilon is the permittivity of the dielectric material. Here dielectric is there. A is the cross-sectional area of the plates and D is the difference between the two plates. Right. This you have and this you know. Today we will see that whenever we consider a PN junction, there in a PN junction, also we observe capacitance. This capacitance existed there due to the structure as well as the presence of the depletion region, which is the responsible one. So let's see how we can observe this capacitance. I'm mentioning here there are two capacitance. One is junction capacitance or transition capacitance or depletion capacitance. Three names. I'm writing only junction capacitance, transition capacitance, or depletion capacitance. The next one is diffusion capacitance. Another one is diffusion capacitance. So there are two types of capacitance which is observed in a PN junction. One is depletion capacitance and another one is diffusion capacitance. Let's move on with this first one, which is depletion capacitance or transition capacitance. The transition capacitance I'm writing here. This is nothing but depletion capacitance, transition capacitance, or depletion capacitance. Transition capacitance or depletion capacitance, which is observed in a PN junction due to the presence of uncovered positive as well as negative charge on both sides of the junction. I'm repeating it again. Depletion capacitance or transition capacitance is present within a PN junction because there is a presence of uncovered positive charge and negative charge on both sides of the junction. I will here show you the positive charge and negative charge. You know that this is nothing but depletion region. And the width of the depletion region we can vary by applying bias. Students, you already learned this PN junction diode under forward bias and reverse bias. Here, these depletion capacitance and transition capacitance or transition capacitance will be observed considering reverse bias. I wanted to inform you why depletion capacitance or transition capacitance is predominant under reverse bias. If we vary the reverse bias voltage, suppose I'm considering the reverse bias voltage is right now here, and with a slight modification, we change the voltage by the amount of dVr. So right now, the reverse bias voltage we apply here is VR plus dVr. So what we'll see, previously, whatever the depletion region width that is existed there, due to the increase in the reverse bias voltage, there will be a increase, there will be a more uncovered positive or negative charge across the junction. What is the effect? Let's first see what is the differential charge that is present there within the space charge region or depletion region in a PN junction. Whatever the lecture material I provide previously, there the variation of the charges as well as the potential and electrical distribution is provided. I consider this axis is rho, which is the volume charge density. So, volume charge density we'll see here, because after that, this one or this one, they are neutral. There is no uncovered positive or negative charge. They are the neutral in and neutral P region. So, what will be the distributions of the charges? The distribution of the charges will be like that. This is the positive charge. So I will consider, suppose this is the positive charge and this is the negative charge for VR. Why I'm doing this in that way, I think clear, because this is the positive and this is the negative. This is the extension of the depletion region with, suppose I consider this Xn for reverse bias voltage VR, and this is 0, origin 0, and this is minus X, extension of the depletion region with on the P sides of the junction. Now what I did here, I increase the reverse bias voltage by the amount of dVr, due to which there will be a net increase in the uncovered positive charge and there will be a increase in the uncovered negatively charged acceptor ion. So this is the differential change which is observed due to the application of additional voltage dVr. So these differential change which is observed here, this is, I can say, dq plus dq because this is the positive charge and this is minus dq. This is the negative charge. And this change is suppose dxn, which is observed due to variation in the reverse bias voltage, and this one is dx. So here I show you that how, based on the change in the bias, the depletion region did vary as well as more charge is observed there across the junction. I here show you the charge density rho back to the concept of capacitance. What is C? C is equal to Q by V. Here, I can modify the equation according to my requirement because this change in the charge we observed here, charge density we observed here, due to the increase in the reverse bias voltage. So I can modify this capacitance equation C depletion is equal to dq dash. I'm just modifying my equation here. This is dq dash, this is dq dash. Otherwise, previously some charges is there. This is dq dash by dv. This dv is the amount of reverse bias voltage we change. Better I should write dv. So what is dq dash, student? In the inside of the junction, this is equal to q in the xn. And in the p sides of the junction, it will be q in a, this will be dxn, sorry, this will be dx. This type of equation I already utilized in your previous classes. So this increase in the volume charge density, this minus sign has no such meaning. It is just only present because of the negatively charged acceptor. I here concentrated on the magnitude, so I should write mod. Okay, mod of dq dash by dv here. So dq dash is equal to q n d dxn is equal to q n a dxp. Now, this differential charge, which is dq dash, why present? Because of the reverse bias voltage is increased. Reverse bias voltage is increased by the amount of dv here. You can see this. This increased reverse bias voltage dv here is the responsible one for this differential charge. So here depletion capacitance is the ratio of this two dq dash by dv here. So what will be the unit? What is the unit of dq dash? dq dash is coulomb per centimeter square. And what is the unit of V? Volt. So what will be the unit of C depletion? It will be farad per centimeter square. C by V, the farad per centimeter square. Now the next question is, yes, you write, ma'am, this equation, but what will be the exact equation of C depletion? For this one, we will move with some derivation. If I just put C dip in that way, which is dq dash by dv here, and here considering only the magnitude, so what will be this? If I'm considering inside, because both are same. So it will be q in the dxn by dv here. So what is xn? We need to take the derivation of xn. Now, you most probably notice what is xn. I already derived this previously. What is xn? See that? This is the xn, student. 2 epsilon is dbi by q na by nd 1 divided by na plus nd whole within the square. But whenever we consider depletion capacitance, we consider that the PN junction is subjected to the reverse bias. So we need to modify the equation. Where should be the modification? Here. What will be the modification here? This will be VBI, net potential will be VBI plus VR. You know this, so I'll write here 2 epsilon S okay, first better I should write this. Xn is equal to 2 epsilon S VBI plus VR divided by Q Xn. So it will be Na by Nd 1 divided by Na plus Nd whole within the square root. This is the equation of the depletion region width along the inside of the junction. So we will take the derivation because this is d with respect to dVr of Xn. Let's take the derivation. What will be CD? CD under such a case will be equal to Q in D 2 epsilon S by Q Na by Nd 1 divided by Na plus Nd dds of x to the power n. So n into x to the power n minus 1. So half minus 1. Okay. There is no such issue. So if you just rearrange the equation, you will see this is minus substudent. This section will be in the denominator. So I will write this Q epsilon S in ND divided by 2 dBi. Sorry, I forget to mention here dBi plus VR. So I should write this dBi plus VR ddx of n into x to the power n minus 1. So dBi plus VR. And this is Na plus n. And this will be whole within the square root. So this is the depletion capacitance which is observed in a PN junction under reverse bias. This is equal to Q epsilon S Na Nd divided by 2 dBi plus VR Na plus Nd. If you have any problem related to the derivation, because I make lots of step jump here, then inform me in your next class. What I wanted to mention, student, remember this equation. This equation is very, very important, and you need to utilize this equation for the solution of lots of numerical problems which came there in your semester exam. Similarly, what I did for N side of the region, I can also take the derivation for the P side of the region, and I will, under such a case, will obtain similar type of equation. What is the similarity here? Similarity is that if you carefully see the equation of Xn, suppose I'm writing here E taken to epsilon s dpi plus dr by q Na by Nd 1 divided by Na plus Nd whole within the square root, and xp is equal to 2 epsilon s dbi plus dr by q Nd by Na. This will be Nd by Na because it is xp. Nd by Na 1 divided by Na plus Nd. You will see that xn plus xp is what? Xn plus xp is that in the denominator there is a term for w. 2, I'm writing w, is w. W is equal to 2 epsilon s dbi plus dr divided by q Na Nd Na plus Nd. This is w, student. I derived this already. So it looks like this one similar to epsilon s by w. That's why not called. I wanted to show you xn and xp. See that? So whatever the capacitance we observed in a PN junction under reverse bias, which is depletion capacitance, this depletion capacitance is very much similar to the parallel plate capacitance, which is observed in a parallel plate capacitor. Don't become confused, student. Here I told you the unit is farad per centimeter square, so it is the capacitance per unit area. Now, if you remove this area, then here a term will be there in the numerator. So it is similar to the parallel plate capacitance, which is observed in a parallel plate capacitor. What is W? W, you know, it is the depletion region width which vary as a function of reverse bias voltage. So what we observe, students? We observe that whenever we consider a PN junction under reverse bias, due to the variation of the depletion region width with reverse bias, we observe a similar form of capacitance across the junction. Now, I here consider two-sided junction, but you can consider one-sided junction. One-sided junction is what? Na is greater than Nd, or Nd will be greater than Na. Anyone. If Na is greater than Nd, what do you know? Heavy doping. So width of the depletion region on that side will be very small. So I will assume in this case xn will be equal to W, because on the p sides of the junction the doping concentration is very large. The extension of the depletion region width on the p sides of the junction will be very small, and I can assume the total depletion region width will be almost equal to the depletion region width on the end sides of the junction. Same thing I can do this here also. I will assume under such a case the extension of the depletion region width is xp, where Nd is much greater than Na. Student, this type of junction is T plus N, and this type of junction is Pn plus. So this is a one-sided junction, student, and in this one-sided junction, you can also modify the equations of CD, where you need to consider again Na greater than Nd. So if you consider this equation here, if I suppose consider P plus N, so Na is greater than Nd. So here Na is greater than Nd. So I will assume only Na is present. This Na and this Na cancels. So what will be the C depletion equation? P epsilon S Nd divided by 2 Vbi plus Vr, polar within the square root. So I'm writing it here. You need to modify your equation. I'm just showing you because sometimes numerical problem not came directly. One state of equation needed to be modified slightly to get your solutions. Q epsilon S I share Nd divided by 2 Vbi plus Vr whole r within the square root. This is for P plus N junction, student. Similarly, if you consider N plus P or P N plus junction, this equation CD under such a case will be equal to Q epsilon S Na divided by 2 Vbi plus Vbi plus Vr polar within the square root. So this is one-sided junction capacitance, one-sided abrupt junction capacitance. This is abrupt. You can see this because the charge density, whatever I draw here, abruptly the changes is observed. Right. That's why this is abrupt junction. If it becomes linearly graded junction, then that type of charge density variation I discussed. I think it is clear what I draw. Otherwise, for abrupt junction, this is the variation of the charge density is x and it is rho. Student, I think you remember this. This is called linearly graded. Linearly, the charge density vary here, and this is for step graded or abrupt junction. So here I consider one-sided abrupt junction. Now here I wanted to validate one point. Suppose I'm considering this equation. C depletion is equal to Q epsilon S Nd divided by 2 dVi plus Vr polar within the square. Now suppose I can write down this expression in that way by removing the square root terms. That will be equal to 2 Vvi plus Vr Q epsilon S Nd. From that equation, I can conclude 1 by C depletion square is proportional to here. The series, rest of the other terms are constant. Epsilon S is the permittivity of the material, epsilon naught into epsilon R. Epsilon R is the relative permittivity. Epsilon 0 is the free space permittivity. You know, donor impurity concentration is Nd. Vbi is the contact potential. Only Vr is subjected, Vr can be varied. And I can conclude that 1 by C depletion square is proportional to Vr. That means there is a dependency of the capacitance with the reverse bias voltage, and if I just plot this, I'm just doing this in my left hand side, that I can use this equation. So I'll assume, suppose this is 1 by C depletion square, and this side is suppose here. So it will be straight line like that, and if you extrapolate the curve, the negative gear direction, you will get contact potential or built-in potential. So here I just plot the inverse capacitance squared as a function of reverse bias voltage, straight line, and I get the point it is built-in potential or contact potential by extrapolating the curve, this particular axis, this particular straight line, the negative x direction, and I find the point where 1 by C depletion square is 0. So this is one another way how you can get the contact potential by doing some experiment. In the experiment, we will observe the variation of the capacitance as a function of reverse bias voltage, and after that you will get this type of characteristic curve in your graph paper, and after that get the contact potential. You will extrapolate the curve in the negative x direction, and you will intersect the negative x axis to obtain the contact potential or built-in voltage. So what is the slope of this curve? The slope is 2 by 2 by q epsilon s. Q epsilon s indeed. This is the slope. So what you observe, there is a variation in the capacitance across a PN junction with reverse bias voltage. This property is being adopted for the design of Varactor diode. Varactor diode is one special diode whereby varying the bias, we can vary the capacitance of the diode. Varactor, that means variable reactor. Laterally, you know this, you read this in your diploma. Varactor, variable reactor, means it is a device whose reactance, in this case capacitance, can vary in a controlled manner with bias, with DC bias. So Varactor diode is a special type of diode whose capacitance can be varied in a controlled manner with bias voltage. Varactor diodes are widely used for the mixing purpose, for the detection purpose, for the harmonic generation, or voltage variable time tuning purpose it is utilized. If I give you an example, that will be much more clear. Voltage variable tuning, you in your daily life you utilize this type of tuning. I don't know whether you see radio or not. Previously, whenever we try to fix a channel in a radio, we vary the tuning knob for the selection purpose of the channel in a radio. Whenever we change the channel selection knob, we actually change the capacitance inside the circuit by varying the voltage. By doing this, we change the capacitance. That means whenever we will utilize the tuning circuit, in the tuning circuit, whatever the tuning frequency is there, that tuning frequency is dependent on the capacitor. So by changing the capacitance, we change the tuning frequency. You learn tank circuit in your circuit theory. So I think there is no need to mention how it can be varied. It is a common example which you observe. So this is the application of Varactor. Now your question may be, ma'am, why we will not utilize discrete capacitors? Discrete capacitors are bulky for a very large value of capacitance. And here in the case of Varactor, by just only considering one diode, the size is very small, we can vary the capacitance offered by the diode. That's why Varactor diodes are adopted. I wanted to inform you one point here. For such types of application, the forward biasing must be avoided, because if you provide more forward bias, whatever the excessive current which flow due to the reduction in the depletion region width, that is undesirable for that type of capacitor. Students minutely observe this. I here show you the variation of the capacitors as a function of reverse bias voltage. So whenever we design Varactor diode, we need to be very careful. We will consider the Varactor diode only under reverse bias. No forward biasing must be provided. Forward biasing must be avoided here. We don't provide the forward bias. So this is Varactor diode. Let's move with the design of Varactor diode, because it is given in your syllabus briefly. Varactor diode symbol. This is diode symbol, student, and capacitor symbols is like that. So this is the symbol of Varactor diode. If we consider one-dimensional equation of Poisson, then this is d square psi by dx square is equal to minus q n divided by epsilon s. N is the generalized doping distribution here. It is actually negative for donut. Now, if we consider it is a heavily doped junction, one side is heavily doped and the other side I can ignore. I'm suppose considering the generalized doping profile is B x to the power m. Why I consider x to the power m? Because if x is 0, m is 0, let's see that if m is 0, then n is equal to x to the power 0, 1. So B, so it is a constant doping profile. If we consider m is equal to 1, then n is equal to bx. So the doping concentration we can vary. If we consider m is 0, n is equal to b means it is uniformly doped throughout the junction. Uniform doping concentration is being maintained, right? Uniform doping. If we consider m is equal to 1, that means it is linearly graded. Bx with x it varies, so it is linear form of grading, so it can be varied. Now, most important is which one that I wanted to inform you here, which is adopted here. If m is less than 0, this type of device is called high power abrupt junction. I not previously mentioned this type of junction of this name. So what is hyper abrupt junction, students? I draw the variation of the doping concentration, then it will be much more clear. So I wanted to plot it. Suppose I consider this is X and this is N. So if M is 0, then this is constant. It is for 0. If I consider, suppose, linearly graded, that means somehow in that way this will vary. This is a 1, M is 1. If I consider M is minus 1, then what will be the nature? Like in that way, that will vary. It's opposite of that. If I consider M is equal to 2, then it will be just like that. If M is minus 2, suppose I'm considering minus 3 by 2, then it is like that. Why I'm considering minus 3 by 2, I'll explain you later. Minus 3 by 2. These such types of values of M, this is actually minus 2. You can see this variation of doping concentration where with X, the doping concentration decreases. These types of junction is called hyper-abrupt junction, and hyper-abrupt junction can be achieved, the process, hyper-abrupt doping profile can be achieved by using epitaxial process or by considering ion implantation. What is epitaxial process or what is ion implantation? I'll discuss it later because fabrication processes are included in your syllabus. Now, if we integrate the Poisson's equation, considering the boundary condition, we will obtain the depletion layer width as well as difference capacitance per unit area. I'm not deriving this totally because my interest is only the final expression. Total derivation is not required here. Whenever we need to take the integration, we need to consider the boundary condition so that we can calculate the constant of integration. Here I am considering the boundary condition. The boundary condition I am considering by putting x value 0. Whenever x is 0, psi will be 0. Whenever we consider x, suppose maximum depletion region with suppose a particular voltage of VBR, then x value will be equal to WD and psi x will be under such a case will be equal to VR plus VBI, or you can write psi VBI. Actually, this is d squared pi by dx square. So there is no such issue. Sorry, I forgot to mention psi VBI. Okay, so this is the built-in potential. I here write down in that way so that I can differentiate this. This is some different form of diode. My objective is to calculate the depletion region width and this differential depletion capacitance. I'm writing the final expression, student. You memorize this. It will be equal to epsilon s. There is no need to take the derivation. If you follow the earlier procedure, you can get the depletion region width. Each and every time it is not possible for me to discuss the derivation. Also, this derivation is not included in your syllabus. It is not required. This will be epsilon s m plus 2 here plus psi VBI divided by QV. V is a constant, student. This value will be decided based on the doping profile. 1 divided by m plus 2. And CD is what? Is epsilon is by WD, and it will be equal to QB epsilon S m plus 1 divided by m plus 2 here plus psi VI 1 divided by m plus 2. Or in another way, I can write CD is proportional to VR plus psi VPI to the power minus some constant term where S is 1 divided by m plus 2. Why I'm writing this? Because you may be confused, ma'am, whenever there is no such requirement, why you are discussing this? Yes, there is a requirement to explain this one. What is S? S is this one or this one, 1 by m plus 2. Now, if you see this equation very carefully, you will see as much as the S is large, the variation of the capacitance with the bias voltage will be much more. How S can be made large? Because we see larger S means larger will be the capacitance variation with bias voltage, right? If S is large, that requirement must be fulfilled by considering hyper-abrupt junction profile. I can explain you. Suppose I consider linearly graded junction. Linearly graded junction means m is equal to 1. So what will be the value of S? S will be 1 by 3. Right? And 1 by 1 writing the variation of S with M. Next, suppose I consider abrupt junction. So abrupt junction means m is equal to 0. So what will be the value of S? S is 1 by 2. See how the CD is varied. Okay. Next, suppose I consider m is equal to minus 1. So if I consider m is equal to minus 1, then S will be equal to 1. If I consider m equal to minus 3 by 2, which I already utilized during figure, during the drawing, minus 3 by 2. So here this is minus 3 by 2. That means it will be, S will be 2. Right? Just see that type of variation. See, whenever m is minus 3 by 2, S is 2. So the variation of the depletion capacitance is very large compared to this case or this case. Fine. That's why whenever we choose the design of Varactor diode, we consider hyper-abrupt doping profile. You can change the m. You can consider m is equal to minus 5 by 3. On such a case, you see minus 5 by 3 here. So minus 5 by 3, that means S is equal to 3. You see, S further increases. So whenever there is a requirement to design Varactor diode, we will adopt hyper-abrupt junction profile because the sensitivity of this capacitance is high here. Sensitivity you can design, I mean you can calculate the sensitivity. What is the time? Almost close. Okay, I'm just doing the sensitivity here. Okay, the sensitivity can be defined, which is the characterizing parameter for a Varactor diode, by considering differentiation of the capacitance with respect to here. That means minus d CD by CD I can consider here, so that I can get proper value of S, CD, CD, VR by dVR, which is nothing but this nothing but it is the logarithm of CD by D of log VR, that will be equal to 1 by m plus 2, which is nothing but S. That's why I provide S here. So the sensitivity S is very much large whenever we adopt hyper abrupt pipe, and generally it is desired one because we wanted to vary the capacitance by using the variation in the reverse bias voltage. So students, this is Varactor diode. Equivalent circuit of Varactor diode is like that. Capacitance, there will be a resistance in parallel. This is the CJ. CJ is the junction capacitance. One resistance will be there. This is RS. RS is the series capacitance, resistance, and RP is the parallel resistance. It's totally dependent on the generation, recombination current, diffusion current, and surface leakage current. That's why this RS and RP is included. CJ and this CJ, this is the junction capacitance, and this RS decreases this CJ and RS decreases with here the reverse bias voltage, and this RP increases with VR. That's why they're connected that way. This is all about depletion capacitance, students. Time is not there, so I'm not being able to discuss today diffusion capacitance. I'll discuss this in your next class. I'll provide the lecture material. Give your attendance quickly. Just a minute, I'm opening your attendance.